Hey everyone, and welcome to today's Explainer. We're jumping straight into one of the absolute most stubborn hurdles in generative AI today. We all want our AI models to think longer, reason deeper, and solve much more complex problems. But historically, giving an AI more time to quote-unquote think has meant it inevitably runs out of space to store those thoughts. Well, today we're diving into a fascinating state-of-the-art research paper from Qualcomm AI Research that proposes a truly brilliant solution, giving generative AI the power to think longer without totally blowing up our hardware limits.
So here's a question for you. Does making an AI smarter always require massive amounts of memory? We've kind of been conditioned to think that scaling up AI capabilities, especially its ability to reason through multi-step logic, requires an exponentially larger amount of memory. It's the classic trade-off, right? If you want the model to ponder a complex mathematical proof, you need massive GPUs to hold all that intermediate computation. But what if we could decouple the depth of an AI's reasoning from its memory consumption entirely?
Okay, here's our roadmap for today. First, we'll look at the AI memory bottleneck, then the looped transformer dilemma. After that, we'll introduce the MELT solution, check out how they actually train this new architecture, and finally, we'll wrap up with the state-of-the-art results.
Section 1. The AI memory bottleneck and defining the KV cache. Let's set the stage with the core technical concept at the heart of the problem. To get why AI literally runs out of room to think, we gotta talk about the KV cache. That's the key value cache. When a standard large language model generates text, it looks back at everything that's already been said. To avoid recalculating all those past words or tokens, every single time it generates a new word, it stores their mathematical representations in the KV cache. Now, it's a fantastic shortcut for speed, but here is the catch. In standard models, this cache grows linearly with every single new step or reasoning iteration the AI processes.
Think of it like a giant math problem on a whiteboard. Imagine a student working through a really long, complex equation. In a standard setup, every time the student finishes a single step of the equation, they write it down on a whiteboard. But instead of erasing the irrelevant parts or just updating the current board, they actually go out and buy a brand new whiteboard for the next step, all while keeping the old ones. If the problem takes 10 steps, they need 10 whiteboards. 1,000 steps, 1,000 whiteboards. Eventually, you literally just run out of physical room in the building. And honestly, that is exactly what happens to an AI's GPU memory with the KV cache.
Moving on to Section 2, the looped transformer dilemma and the cost of deep thought.
So researchers knew they needed to give models more time to think implicitly, without just generating endless chains of text. That brought about looped language models, like one called Uro. The idea is brilliant. Pass the data through the same transformer layers over and over again, allowing the model to refine its answer and effectively think deeper. It works beautifully for reasoning, but there's a crippling limitation. Because they use standard KV caches, their memory still grows linearly with every reasoning loop. They are buying new whiteboards for every loop. The dream scenario, what researchers really want, is an architecture where memory stays completely flat no matter how deep that reasoning goes.
Just to put this into perspective and show how severe this bottleneck is, let's look at some numbers for the Oro model. If you ask a relatively small 1.4 billion parameter Oro model to process a sequence of 32,000 tokens, it eats up a massive 27.97 gigabytes of memory just for the KV cache and model weights. Almost 28 gigs for a small model that is incredibly expensive. If we want AI to think for minutes or hours before answering, this linear explosion in memory makes it practically impossible to scale up.
Which brings us to Section 3, introducing the MELT solution, and what I like to call the smart eraser.
Meet the memory-efficient looped transformer, MELT. Here's the absolute game changer. Instead of expanding the cache by appending a new state at every single loop step, MELT maintains one single fixed-size KV cache per layer that is shared across all reasoning loops. Going back to our analogy, MELT gives the AI a single permanent whiteboard for the entire math problem. Instead of buying new whiteboards, the AI just updates the one it already has.
But wait, right? If you only have one whiteboard, how do you know what to erase and what to keep without messing up the math? That is where the learnable gating mechanism comes in. Think of this gate as a smart eraser. At every single loop, this gating mechanism dynamically looks at the new information and the old information, and it mathematically decides what to overwrite, what to blend, and what to preserve in place. It shifts the entire burden of retaining information away from just mindlessly storing everything and puts it onto a highly intelligent, dynamic system.
Section 4. Training a new architecture, or how they tamed the beast.
Now, this all sounds amazing in theory, but rewiring an AI's short-term memory completely breaks standard training pipelines. Because Melt's single cache relies on updating sequentially over time, standard parallel training just breaks down. So the researchers had to invent a completely new two-phase, three-step training process to tame this beast. First up, chunk-wise training, then an interpolated transition, and finally, attention-aligned distillation.
Basically, to make this work, they took a pre-trained looped model and actually faded the old architecture into the new Melt one. They ran both the old expanding cache and the new single cache, linearly blending the model's reliance over time. Once the model got the hang of the single cache, they froze the original model to act as a strict teacher. They forced the Melt model's internal representations to align perfectly with the teachers at every single layer using an attention-aligned distillation loss. They essentially held the model's hand while it learned how to use its new smart eraser.
And finally, Section 5, State-of-the-Art Results. High performance, low memory.
So, did this crazy architectural workaround actually pay off? Oh, absolutely. Remember that nearly 28 gigabytes of memory we needed earlier for a 32K token sequence? Melt drops that exact same reasoning sequence down to a flat 9.49 gigabytes. That is practically a 3x reduction in memory footprint. And because it's constant, that memory won't grow no matter how many times you loop the model to think deeper.
And the performance data gets even better. If we compare Melt against QN3, which is a standard non-looped model of similar size, and Utero, Melt actually beats the standard model on really tough math benchmarks like Math 500 and EP226. It proves its reasoning chops for sure. And while it slightly trails the massive Utero model, it achieves this high-tier performance using just a fraction of Utero's memory footprint. We get the deep reasoning benefits of looping with the incredible memory efficiency of a standard model.
What this data really cements is that the researchers absolutely pulled it off. While standard looped models offer great performance with frankly terrible memory usage, Melt successfully decouples deep mathematical reasoning from extreme memory consumption. It gives us high accuracy with a seriously low memory footprint.
The big takeaway here is a massive triumph for the field. We can finally scale inference time compute, meaning we can let the AI think for as long as it needs to during generation without totally blowing up our hardware limits. This paves the way for running highly intelligent, reasoning AI on much smaller, more accessible devices. The smart eraser works, and that transition training pipeline makes it possible to adapt existing models rather than spending millions to train from scratch.
We're stepping into this incredible era where AI won't just blurt out the first thing that comes to its mathematical mind. It'll pause, it'll reflect, and it'll reason through deeply complex problems using a constant, super efficient memory footprint. So, I'll leave you with this. What does the future of AI look like when reasoning depth is no longer chained to memory limits? It looks incredibly bright, and thanks to models like Melt, it's a whole lot closer than we think. Thanks so much for joining me on this explainer. I hope you found it as fascinating as I did. Keep learning, and I'll catch you next time.